Hello! In this video I wanted to present to you my latest device, the OCXO Controller. An OCXO, shorthand for Oven Control Oscillator, is a very precise oscillator which is used to generate very steady pulses, and what we are going to see in this video is how to sync it with an external signal. We will discuss how to naively discipline clocks and the different techniques I've used to create the OCXO Controller. Before we go ahead, let's do a very fast recap. An oscillator is an essential electronic component used to generate periodic pulses. These pulses are used in a myriad of ways in electronics. For example, they can be used as the clock signal for a CPU or a microcontroller. On each pulse, the CPU may fetch data from memory, run an instruction, write to memory. All these sequential operations advance at a rhythm set by the clock signal. An oscillator may also be used to generate waveforms to use, for example, in communications or music. In my case, I'm interested in generating very precise pulses. I need those to test another device that I'm currently working on. Its precision is around 10 nanoseconds, so I want to generate signals which can vary around this mark. Furthermore, I need to know the time at which the signals are being generated. First of all, we have the OCXO. As I've previously said, an OCXO is an oscillator. There are lots of kinds of oscillators, for example, crystals, MEMS, RCs, TXCOs. An OCXO is an oscillator which heats up to a certain temperature, which guarantees that external ambient factors will not affect it. And so it generates a very stable clock signal. This one in particular is an OCXO 143 series from Isotemp. It generates a 5-volt square output of 10 MHz with ±20 ppb. ppb stands for parts per billion. This number is used to represent the stability of an oscillator. Formally, it is defined as the ratio between the frequency deviation of an oscillator and its theoretical frequency. It's this formula right here. But let's try to make a more sensible approach. Let's do a little math. In the case of my OCXO, the frequency is 10 MHz. That's 10 million pulses in a second. Now, they say that for every billion pulses, there may be an extra of up to 20 pulses or a shortage of up to 20. So, by doing a rule of 3, we get that for every 10 million pulses, there can be plus or minus 0.2 pulses. So this OCXO, in a worst-case scenario, can generate 10 million points, 2 pulses a second. Well, that doesn't sound so bad. If we transform frequency into periods, 10 MHz gives a period of 100 nanoseconds. And 10 MHz, 0.2, be that number, gives you a period of 99.99998 nanoseconds. Well, that difference is just ridiculous. But let's put this into perspective, shall we? The difference we saw was 2 to the power of minus 15 seconds. In a day, there are 86,400 seconds, so this clock would be delayed by 172.8 picoseconds a day. For a month, it would be delayed by 5.2 nanoseconds. We could go on and on, but this is what I meant when I said that this clock is precise. It keeps time really well. Come to think of it, I don't really know the real ppbs of the OCXO. I know the range of the ppbs, but this doesn't mean that I know the current ppbs. Oh, and get this, the ppbs may change during runtime. This means that I do not really know the exact frequency of the OCXO at any given time. That's a real problem, because I can calibrate the OCXO in my laboratory using, for example, my oscilloscope, but I cannot guarantee that it will be well calibrated when I take it to another place, which may have different ambiental conditions. We can solve this by syncing our OCXO with an external signal. The idea is that this signal will be really precise and will know all relevant information from it. In particular, we will know the date and time of its edges or transitions, and we'll know its frequency and duty cycle. In my case, I decided to go with the PPS generated from a GNSS sensor, the u-blox Neo M8. This little device receives data from the GPS and GLONASS network of satellites and generates, apart from a precise geological position, a very good PPS, which stands for pulses per second. And normally, when referring to a PPS, we'll be talking about a 1 Hz signal. The frequency and duty cycle of this signal can be configured, but 1 Hz squared is good enough for now. Furthermore, what this device will do is to align its pulses with the time of week, or TOW. This time of week refers to the count of seconds that have elapsed since the beginning of the GPS week, at midnight between Saturday and Sunday. This time is also synchronized with the UTC, or Coordinated Universal Time, which is the primary time standard used around the globe to regulate clocks. To sum up, I will receive a rising edge every second, and this rising edge will coincide with the passing of time in most of the other devices I have around my home. So there we have the time frame of reference I needed. About getting the actual frequency of the OCXO, we can count the number of edges received from the OCXO in between two edges of the external PPS. For example, I receive a rising edge on the external PPS. My device starts counting the OCXO's edges and it stops when another external PPS is received. Let's say that I see that 10,000,001 pulses have been received. From that, we can deduce that the frequency of the OCXO must be really close to 10,000,001 Hz. Easy enough, now I have a way of getting the actual frequency of the OCXO. Nice! So finally, we get to the topic we had in hand. I don't know about you, but I don't like my OCXO to be 10,000,001 Hz. That sounds like a mouthful. I would like my clock to be precisely 10 million Hz. Well, lucky for me, the OCXO 143 has a special input pin called VCO input. A voltage control oscillator, or VCO, is an oscillator whose frequency can be controlled by an external voltage. We can see on the OCXO's datasheet that there's an entry called Electrical Frequency Adjustment, which talks about how to vary the frequency of the clock. Let's see its fields. First off, we have the range property. We can see that its units are ppm, which stand for parts per million. It's the same concept as what we had with ppbs. Its value ranges from plus minus 0.4 and plus minus 1 ppms. And what we can see is that this is reference from nominal frequency. In my case, the nominal frequency is 10 MHz. Let's take the maximum range as an example. If there's plus or minus 1 pulse for every million pulses, there will be plus or minus 10 pulses for every 10 million pulses, thus giving me that the OCXO can be skewed for a maximum of plus minus 10 Hz at best. If we do the same with the 0.4 value, we get that we can skew the frequency plus minus 4 Hz at worst. Second field is called control. That's not a very informative name, but if we look at the units, we can see that these are volts. Its value ranges from 0.0 to 4.0 volts. The next one is slope, telling us that it's positive. Alright, and the next field is center. Again, the units are volts, and its nominal value is 2.0 volts, just in between the minimum and maximum control voltages. From this information, we can deduce the following. By applying a voltage between 0 and 4 volts, we will be able to vary the frequency of the OCXO. If we go over the center, the frequency will increase, and if we go below the center, the frequency will decrease. We can expect the OCXO to vary its frequency linearly, but we don't get much information about it. The next field is called linearity, and its maximum is plus or minus 10%. I think this value is referring to the coefficient of correlation of the curve frequency over voltage. It tells us that this curve can be approximated with a linear function, and in a worst-case scenario, the coefficient of correlation will be 0.1, which is just awful. The last field is input impedance, in kiloohms. This tells us that the pin can be approximated as a 50 kiloohm resistor at worst, meaning that our controller, the one supplying the voltage to this pin, should at least supply, let's see, so we got 4 volts maximum over 50 kiloohm, that's 80 microamps. It's a small amount, but let's keep this value in mind. Well, these values are okay, but again, they are just ranges. Maybe you will be thinking that if I want to thoroughly control the OCXO, I need to know the exact behavior of the device, and that I should calculate a graph of frequency over voltage. Then, to control the frequency of the clock, I will only need to input frequency in the graph to get the desired voltage. But to this I have one catch. If you remember, the real values of the system will change over time. That means that the graph I calculate now may not be real after the device has been running for a few hours. All these changes in the properties can be linked to different factors, which the dataset narrates in the frequency stability section. Ambient, operating temperature, aging, which just means that the pass of time itself affects the OCXO, voltage, warming up time. There are many factors that would have to be accounted for to make the OCXO run as just, I need a frequency, let's input it into this function, and now I know the voltage I need. Furthermore, remember that I want to sync the pulses of the OCXO with the external reference signal too. So how did I do it? Well, first let's hear a word from the sponsor of the OCXO Controller, PCBWay. Whether you're a hobbyist, engineer, or student, I feel confident in saying that PCBWay is the go-to destination for high-quality PCB manufacturing and prototyping. Here are just a few of the reasons why PCBWay stands out. Its top-notch quality. After thoroughly inspecting all the PCBs, I was really content with the great precisions the PCBs and the stencil were made. I felt that they are reliable and durable. It's fast turnaround. The ordering of the OCXO controller and shipping to Spain took around a week and a half, which is most impressive. Affordable pricing. Their competitive rates make professional-grade PCBs accessible to everyone. Its excellent support. From order placement to final delivery, PCBWay's team was always there to answer my questions and provide guidance. Thanks to their expertise and dedication, I was able to turn my ideas for this project into reality without a hitch. If you're working on your next PCB project, I can't recommend PCBWay enough. Visit PCBWay.com and experience their amazing service for yourself. And final thanks to PCBWay for their patronage. On with the video. We were talking about the important question of how to sync the output of the OCXO with the external reference signal, and at the same time control the OCXO's frequency. Well, let's try to pose this problem in a different manner, shall we? Suppose we have two square signals of the same frequency. This red signal will be the external reference, and the blue one will be the OCXO's output. At the beginning, let's suppose that both signals aren't in sync. You can see here that this rising edge is not happening at the same time as this other edge. In fact, the OCXO's edge is happening after the first reference edge. Remember that we cannot modify the reference signal. We can only change the speed of the OCXO's output, and by speed I mean its frequency. So right at the beginning we see that the edges aren't aligned, therefore we must modify the output. The easiest way to do this would be to just move the paper to the left, and the edges would fit. But this movement is not really possible, right? This edge has happened, and once that it has passed, we cannot go back in time and modify it. So, what other thing can we do? Well, if you think of it, we moved the paper to the left, and in doing so we made the edge occur before. So, if the wave had been a little bit faster, this edge would have occurred before, and the waves would be in sync. So we can do just that. We've just seen that if the OCXO's edge is after the reference, we need to speed up the OCXO. Let's do the other case. Let's suppose that the reference edge happens after the OCXO's edge. Well, in this case, what we would do, if we could, is to move the strip of paper to the right. By moving it to the right, we would be making this initial edge happen a little bit later. Therefore, we're slowing down the wave. Fair enough, if we turn down a little bit the frequency of the wave, we'll see that the next two edges coincide. Great! We have learned that when the OCXO's edge happens before the reference, we need to slow down the OCXO. Now, this will cause another problem, and that is that before we had signals of the same frequency. We modified the frequency of the OCXO, meaning that even though we managed to fit these two signals at the same point in time, they will not fit on the next edge unless we modify the frequency again. In the end, what we will end up doing is slightly modifying the frequency of the OCXO until all edges rise at the same time. Notice that by doing this, we are making both signals have the same frequency and the same phase. One more thing to bear in mind. In my case, I said that the reference signal was going to be a 1 pps signal, and the OCXO generates a 10 MHz signal. So there's no way I can compare these two signals. They have to have the same frequency so that I can do the same process I talked about before. The easiest way to fix this is to divide the OCXO signal down to a 1 Hz signal. But how is a clock signal divided? And what does that even mean? When I say that I'll be dividing the signal, what I'm referring to is that I'll be feeding the clock through a digital counter. A digital counter is a circuit which holds a binary number. The circuit increments this number every time it receives a clock pulse. Let's make an example. Imagine a 2-bit counter. With only 2 bits, we can only create the numbers 0, 1, 2, and 3. These are all the possible states that the counter can have. Let's say that the counter is initially at 0. When a clock pulse is received, it will increment its value to 1. Next pulse, and it will reach 2. Another pulse, and it will make it 3. Now, the next clock pulse will reset the clock. That's because the next number after 3 would be 4, but as this number does not fit in 2 bits, you can either imagine that the counter resets, or even that it cuts the third bit of the 4, and only keeps the 2 least significant bits. This is called overflow. In this example, let's take a look at the second bit, the most significant bit. We can see that in states 0 and 1, this most significant bit remains at 0, and in states 2 and 3, this bit is 1. So what we have is that during 2 clock cycles, this line will be 0, and for another 2 clocks, the line will be 1. We have taken the initial frequency, and we have divided it by 2. In other words, the frequency of this line would be half of the original clock frequency. Now we can expand this example even further. If we take more bits, then the clock signal will be divided by an even greater factor. If we have 3 bits, we would be dividing the clock by 4. For 4 bits, we could divide the signal by 8, and so on. If you pay attention to the dividing factors, you might notice that they are all powers of 2. This is because we are using binary counters, or base 2 counters. All divisors will be powers of 2. This is a problem for me because I need to divide the OCXO by 10 million, which is not a power of 2. So what can we do in this case? Well, we can add a comparator at the output of the counter. A comparator is a logical circuit which compares 2 digital inputs, and when they are the same, it outputs a 1. In every other case, it returns a 0. The idea behind using a comparator is that we can create a pulse when the counter has the same value as the other input of the counter. The output of the counter can be then used to toggle a bit on a different circuit, generating the frequency that we want. If we take my 10 MHz signal and we want to convert it to a 1 Hz signal, let's draw it one above the other, how many edges have to pass on the 10 MHz signal before we toggle the 1 Hz line? By the way, I'm supposing for the sake of simplicity that the 1 Hz signal has to have 50% duty cycle. This means that it spends 50% of its period in a high state and 50% in a low state. Easy enough, I guess you can probably see that we need to count for half these 10 million pulses before toggling the signal. Easy enough, I guess you can probably see that we need to count for half these 10 million pulses before toggling the signal. Half of 10 million is 5 million. If we flip a bit every 5 million pulses of the OCXO signal, we'll have a 1 Hz signal. Back to the counter plus comparator we were talking about. Let's suppose that we have a very big counter that reaches the 5 million mark we're looking for. How big should this counter be? In other words, how many bits do we need to write down the number 5 million? Well, this is fairly easy to calculate. Just take the base 2 logarithm of 5 million and this returns 22.25, which would be the exact number of bits we would need to write 10 million. We'll have to round this number to 23, as there's no such thing as a 0.25 bit. If we write 5 million in binary, that will be 100, 1100, 0100, 1011, 0100, 0000. If we count the number of bits, we have 23. Nice! So we need a 23-bit counter, and as we said, we need to generate a pulse when the counter reaches 5 million. This pulse will then toggle a bit, generating the 1 Hz signal we were looking for. About toggling this bit, the device I'll be using for this demonstration is called a T flip-flop. A flip-flop, also called a latch, is the smallest unit of memory in a digital circuit, and it stores a single bit. In the case of a T flip-flop, it has a single input called T, which toggles, and that's what the T stands for, the content of the flip-flop upon a rising edge. The pin Q outputs the content of the flip-flop, and here's where we will find the 1 Hz divided signal. So why don't we simulate how the circuit would work up to this point? The counter starts at 0, and when the OCXO is powered on, it will start incrementing. Now the counter reaches 5 million, and a pulse is generated on the output of the comparator. This pulse will then toggle the flip-flop, generating the first half of the divided signal. But now the counter keeps incrementing. In fact, it will reach the maximum number possible with 23 bits, which is 8,388,607. Then it will overflow, return to 0, and it will reach 5 million again. Now if you pause and think of it, the number of increments that the counter has needed to reach again this 5 million has been 8,388,608 steps, or 2 to the power of 23. From this point onwards, the counter will toggle the flip-flop every 2 to the power of 23 edges of the OCXO clock, which is not what we wanted. We are currently dividing the OCXO's output down to a 0.596 Hz signal, which is not the 1 Hz I was expecting. So what did I miss? The problem comes from the counter. When it reaches 5 million, it should go back to 0 and continue counting from then on. In other words, we need to clear the counter when the comparator fires. Clearing the counter just means setting its inner number back to 0. So I think that now that you have a general image of the circuit, maybe we should write it on paper. This right here is the circuit we've been talking about. On the top, we have the OCXO. On pin 5, I'm powering it at 5 volts as the datasheet reads. I've also added a capacitor on the power rail to mitigate voltage fluctuations which would affect the OCXO. Pin 2 is connected to ground, and pin 1 outputs the 10 MHz signal. Pin 3 is the VCO input. The resistor network that this pin is connected to is a variable voltage divider. Current flows through R1 and R2, creating a voltage drop on each one, as Ohm's law tells us. What we need to do is find the right values of R1 and R2 so that the VCO voltage falls in the range of what the datasheet told us, 0 volts and 4 volts. Notice that the symbol of R2 is a little bit different. This is a potentiometer or variable resistor. In reality, there are 2 variable resistors on R2, which can vary depending on the rotation of an axle. When one of these resistors increments, the other decrements at the same rate. What this value of 1K is telling us is that the sum of the inner variable resistors is always 1K. In the case of this circuit, I only need one of these 2 variable resistances, so I'm shortening one by connecting its both extremes to the same node. Anyways, the VCO voltage, the voltage between this node and ground, can be calculated by this commonplace formula. the voltage at pin 3 will be R2 over R1 plus R2 times the VCC voltage, which in this case is 5 volts. Remember, we have two voltage limits for the VCO, 0 volts and 4 volts. Watch what happens when we set R2's value to its lowest, which in this case is 0. We get 0 volts. Good, we have the lower bound of our control voltage. Notice that when R2 starts incrementing, it does so in both numerator and denominator. Imagine R2 were to be a really big number, so much so that R1's value would be almost negligible. We would see that the numerator and the denominator would be almost the same, meaning this fraction would be equal to 1. Therefore, the control voltage would be VCC. Of course, for this to happen, R2 should be much greater than R1, and we're not really looking to input 5 volts into the VCO. What I would like you to notice is that if we start incrementing R2 from 0, the VCO's voltage starts incrementing too, and we reach the highest value when R2 is the greatest. Okay, if we input 4 volts as the output of the voltage divider, we get the following equation. This equation has two variables, therefore there are an infinite number of solutions to it. If we put it in words, this equation tells us that R2 should be 4 times the resistance of R1. Now we just have to find some values that fit this criteria. Sadly, I don't have much of a variety of resistances in my studio, so I went with the values you see on the screen, which will give me a true range of 0 to 3.4 volts. Side note, for the sake of simplicity, I've supposed that no current will flow towards pin 3. We can justify this by saying that the equivalent resistance of the VCO pin, that is, the resistance between pin 3 and ground, is relatively big compared to R2's. We already saw that this value on the datasheet was 50 kΩ. 50K is bigger than 1K, meaning that most of the current flowing from 5 volts through R1 will go through R2 and not through the VCO pin, because current likes to take the path of least resistance. Some current will flow through pin 3, but it will be negligible compared to R2's. Another side note, this voltage divider is not linear. If we plot this voltage divider formula, we get a hyperbola. If we zoom in the range of R2 between 0 and 1000, we can see a curve which connects 0 volts with 3.4 volts, and not a straight line. This may cause us some trouble to fine-tune the VCO's voltage, but hey, we're engineers, this looks flat enough for me. Jokes aside, if we limit ourselves to very small variances of R2, for example, let's plot the same graph but for R2 values between, let's say, 800 and 900 ohms, we can see that now the line looks decently flat. And this is what engineers do when they try to linearize systems. Small variances on the input of a system should cause small variances on the output, and these should be proportional to each other. This is not always the case, but we engineers strive to flatten everything as much as possible. And well, at least me. Let's continue with the rest of the schematic. Right below the OCXO, we can see 3 binary counters, U2, U3 and U4. I've chosen the SN74HC393 from Texas Instruments. If we take a look at the datasheet, we can see that these chips are dual 4-bit binary counters. In other words, a single IC has 2 binary counters of 4 bits each. We can see at the bottom of the page the logical diagram of each of these counters. On the left, we have the inputs CLR, which stands for clear, and CLK, which stands for clock. They are connected to buffers, which are these little triangles right here. But notice that they are not the same. Clock's triangle has a little circle on the left, which means it's an inverting buffer. A buffer is a simple logic gate which isolates the inputs and replicates the input signal on its output. In the case of inverting buffers, they replicate the opposite of the input. When they receive a 0, they output a 1, and vice versa. An inverting buffer is also commonly called a NOT gate. Going back to the diagram, we see these 4 boxes with inputs R and T, and a single output Q. They don't tell us much of what they mean, but we can take a guess and say that as R is connected to the clear signal, it must mean reset, and knowing that this is a counter, and bits get flipped on each clock's edge, the T must stand for toggle. Therefore, what we're seeing here is a T flip-flop. We have already discussed the T flip-flop, so let's try to think about the behavior of the 4 flip-flops working in tandem. Let's start by drawing a possible input for the chip. Let's say we first clear the counter so that it starts with QA, QP, QC, and QD at 0. After that, let's just input a clock signal and see what happens. In the beginning, we don't really know the values of the Q outputs, so let's leave it crossed, like so. When the clear rising edge occurs, we can settle Q outputs to 0. This happens because the clear signal gets replicated by the buffer and enters the R input of each flip-flop, setting its content to 0. Now, the first rising edge of the clock is received. On the other end of the inverted buffer of the clock signal, we get a falling edge, which does nothing to the first T flip-flop, as this little triangle here indicates that it is activated by a rising edge. If it was activated by a falling edge, it would have a circle like the other 3 flip-flops. So the first rising edge goes on and nothing happens. So now here comes the falling edge. After the NOT, we get a rising edge, and this toggles the first flip-flop, setting QA to 1. This change of QA from 0 to 1 generates a rising edge, but it does not affect the second flip-flop, as it is activated by a falling edge. Next clock cycle happens, and on the falling edge of the clock, QA gets flipped again, from 1 to 0. This falling edge toggles the second flip-flop, setting QB to 1. Notice that it took 2 clock cycles to generate a change on QB. We can keep simulating this, and after another 2 cycles, we get a falling edge on the second flip-flop, which causes the third one to flip to. Again, notice that it took 4 clock cycles to generate a change on QC. I guess you already know what's going to happen. After 8 cycles, QC gets set to 0 and toggles QD. Another 8 cycles later, QD would fall back to 0, and this would set us again on the initial state of the simulation. What would happen if the output QD was connected to another T flip-flop? Well, we're moving in powers of 2. QA toggles every cycle, QB every 2 cycles, QC every 4 cycles, QD every 8 cycles. The next flip-flop will toggle every 16 cycles. Now, what if we connect QD to the CLK signal of a different counter? Would it work the same as putting another flip-flop down the chain? The answer is yes. That's exactly the reason why the clock signal has an inverting buffer at the beginning. It is so that we can daisy chain these counters, which just means connecting one counter's QD output to the clock input of a different counter. Before we move on, remember that we wanted to divide the OCXO frequency, so we should be sure that we can input the OCXO's clock signal into the counter. Let's take a look at the dataset. Right, so in section 4.5, we can see that if we power the counter with 4.5 volts, that maximum clock frequency would be 25 MHz, which is above the 10 MHz of the OCXO, so we're good. By the way, why am I taking the 25 MHz value instead of the 31? This left column tells us about the behavior of the chip at an ambient temperature of 25 degrees Celsius, and the column up the right just says the name of the chip. We should take this information on the right as the worst case scenario, maybe when the chip is near its extreme operating temperature. And we as engineers should always prepare circuits for the worst case scenario, therefore always taking the most restricted values we see in the dataset. Although that's just my recommendation. Now that we got the counter sorted out, let's go back to the circuit. We can see that I've connected all QD outputs to the clock input of the counter to its right. In effect, I have daisy chained 6 4-bit counters, giving me a counter of 24 bits. Remember, we needed 23 bits to write the number 5 million, so we could convert the 10 MHz into a 1 Hz signal. You can also see that I've connected the clear signals together to the counter clear net, and I've also added a 10 kΩ pull-down resistor. The pull-down assures us that if the power source which toggles the counter clear signal gets disconnected from the circuit, the voltage of the line remains at 0. In other words, this prevents the accidental clearing of all the counters. Its value, 10 kΩ, is just a good rule of thumb. for pull-down resistors of TTL signals. We have our counter. Now we just need to create a logic that resets it every 5 million pulses, which is what this next circuit does. Here on the left, we have a column of 4 ICs named SN74HC393 and E4. Let's search on the internet about its dataset. It tells us that it is a quadruple 2-input exclusive OR gate. An exclusive OR gate is really handy for comparing 2 bits. Its output is 0 when both inputs are the same, and 1 when they are different. In section 8.4 we can see its truth table. This chip has 4 exclusive OR gates, allowing us to compare up to 4 bits. By using 4 chips, we get to compare 16 bits. If we take a closer look at U5 for example, by using 4 chips, we get to compare 16 bits. If we take a closer look at U5 for example, we can see that on the A inputs I have connected the individual bits of the counter from the previous schematic. On the B inputs I have connected some new signals named I. These inputs come from this other schematic. Here we see an awful amount of resistors connected to the I signals we were discussing. And they are all connected to SW1 and SW2, which are these small dual inline package switches, also called microswitches. The other end of the microswitch is connected to ground. When we close the switch, we connect the I signal to ground, meaning that we set the logic value of I to 0. If we open the switch, the I input gets connected to 5 volts through the pull-up resistor, meaning it will be a logic 1. The individual outputs of the 4 exclusive OR chips are fed to these middle chips, the CD74HC30E. If we search for them, we can see that they are single 8-input NAND gates. NAND stands for negated AND. A NAND gate outputs 0 when all inputs are 1, and 1 otherwise. It's the opposite output of an AND gate. In the case of the U6 NAND gate, it operates on all 8 inputs from the exclusive OR U5 and U7. Only when all the outputs of the XOR are 1, the NAND gate will output a 0. In the rest of cases, it will output a 1. To put it in words, when the numbers match, the XORs should all output 1, so that the NAND outputs 1. This is a little counterintuitive because the XOR outputs a 0 when the bits match, and not 1, which is what we want. The solution is to set the inverse of the number we want in the microswitches. When all bits of the number on the counter and the microswitches are opposite, the XORs will output a 1, and the NAND gate will output a 0. And the same is done in U10 but using the bits from U9 and U11. Now we have 2 separate comparators, U6 and U10. We have to mix the signals so that we get an edge only when they are both at 0. Therefore, we want a 1 only when both U6 and U10 are giving away at 0, and this is called a NOR gate. The SN74HC393 is a quad 2-input NOR gate IC, which will output 1 only when both U6 and U10 output 0. Okay, let's recap. We wanted this comparator circuit to reset the counter when it reaches the 5 million mark. We are comparing the output of the counter to a set value, in our case 5 million, and when both numbers are the same, we trigger the reset of the counter. Also, remember that we were going to feed the counter clear signal to a toggle flip-flop, and this was going to be the divided OCXO signal. Well, you may see on this schematic that I've connected the counter clear to the clock input of another counter. This may seem strange, but remember that inside the counter there were 4 T flip-flops, so what I'm doing here is using the top flip-flop as the final divided OCXO T flip-flop. It may seem a little overkill, but I don't have T flip-flops in the studio. One other thing, this circuit is supposed to compare the OCXO's counter to the binary number 5 million, but 5 million needs 22 bits to be written. Therefore, we cannot compare this number using only a 16-bit comparator, right? Okay, let's write 5 million in binary. Now, Imagine the previous number, let's write it too. Now let's compare the two from left to right. We can see that the first 16 bits are the same, and when we reach bit 6, we find the first bit change. Okay, now I ask, which numbers contain the first 16 bits and also the 6th bit? Well, we can write them and they would be the next numbers after 5 million, right? Now consider the following. If we're going to reset the counter at 5 million, are these following numbers going to happen? Is the counter going to generate them? Well, no, right? We're resetting at 5 million. There won't be any 5,000,001, nor 2, nor 3. So this number 5 million, which occurs when the counter outputs these bits, is only going to happen once, and we don't care about the following numbers after it. So we just have to be prepared when the first 17 bits of 5 million are output. Therefore, we only need the first 17 bits to be compared to generate our counter reset pulse. 17. We are 1 bit short. The easiest way we can add a bit to the comparator is to add another input to the final NOR gate. We can connect to it the most significant bit, which in our case for 5 million is bit 22. The issue I have is that I don't have a 3-input NOR gate, so we have to adapt the 2-input gate we have. So, gate 1 is doing the operation we talked about before, right? It's taking U6 and U10 and is operating with an OR gate, right? Good. Now, what I want is to add D22 in the sum. So we want something like this. But remember that D22 is active with a 1, and U6 and U10 are active with a 0, so we have to convert D22 from active high to active low. And for that, we just have to negate it, right? Okay, so this is our objective. And on gate 2, you can see that we're inputting D22 on inputs A and B. So what this is doing is this operation right here. And this is the same as D22 negated, okay? So this cable right here is D22 negated. And then we're doing basically the same on gate 4. We're inputting twice U6 plus U10 negated. So what we're going to get from pin 13 is U6 plus U10. And on the output 3Y, what we're doing is summing D22 plus U6 plus U10, and we're negating it. So yeah, this is basically what we get by connecting these cables.